Alright guys, we're going to attempt a video here. This is graphs of basic trigonometric functions, part 1. You should be on page 183 in your workbook, and we're going to go through this. You should have your calculator with you and your workbook with you and a pencil, and let's see how this goes. So this starts off with some of the graphing that we did in class earlier, and if we are going to graph y is equal to sine x, it's going to look a little bit like this. We've seen this before, so let's go ahead and put that into your calculator. Press pause, type that into your graph screen, and we're going to graph this. You should be in radian mode for this one. And our window settings, we have them on the graph, and so you can go from negative 2 pi on the left to positive 2 pi for your x window settings, so that you're going to change your x min and your x max to accommodate those. Your y min and your y max, let's go from negative 2 to positive 2. Always going from the leftmost point is your x min, your lowest point is your y min, and then going left to right and from down to up. You can also use this, that you can set it, go into viewing window on your Casio, and then hit your trig. On your TI, hit zoom and then zoom trig. That will change you. You're going to get settings that are approximately like this. Alright, so when we're ready to graph this, we're also going to be able to graph this by hand eventually. And it's going to end up looking like that. This. We're going to have at 0, 0, we'll have a point. We're going to have a maximum, and you should be able to find that on your calculator. To find a maximum point is at pi over 2, comma 1. Sine of pi is equal to 0. Sine of 3 pi halves is equal to negative 1. And all of these points are going to look like this. You're going to have this graph that looks like this wave that we've seen before. But we can also graph this by having all of these points in like this. If you think about it, think about what's going on with sine. Remember that sine is the y values, and sine is, let's see here, sine is positive when it's up and it's negative when it's down. And so if we think about it that way, sine of pi halves at this point up here, that's 90 degrees. Sine of pi halves is positive 1. By the time it gets down to 270 degrees, or 3 pi over 2, that ends up being negative 1. And this is going to look like this, a nice smooth curve. That goes through all of those points. It looks like I missed negative pi, but it's going to go through all those points. It's going to be a nice smooth curve. It approaches the maximum and the minimum almost at horizontal, and it's almost flat going in and coming out of those points, and it ends up being this nice smooth curve, and it's going to look like that. Our domain, of course, you could take sine of any angle, and so x, such that x is an element of the reals. There's our domain in set notation. Our range would be y, such that y is an element of the reals. No, it's not. Sure it isn't. Whoa. What the heck? Haha. Okay, here we go. What is our range? Our range is, it has a lowest point, lowest height of negative 1. It has a highest height of positive 1. These are our y values, and so it is all the values in between and equal to. Negative 1 is less than y is less than 1, comma, y being an element of the reals. Whew. All right. So here we go. Let's work on this for cosine. So we're going to delete that graph. We're going to look at the graph of cosine. Remember what cosine looked like. Cosine looked like this, and cosine looked like, when we had our unit circle, cosine was positive over to the right and it was negative over to the left. And whether you remember this by the cast rule or whichever, that's what we have going on. So at 0 degrees, cosine is all the way over here. Cosine is measuring its x value, and so cosine of 0 is positive 1. At 90 degrees, or pi over 2, it has a left-rightness of, that's not really a word, of pi over 2 is equal to 0. So cosine pi over 2 is 0. Cosine of pi, and you can confirm all of these on your calculator. Cosine of pi is negative 1. Remember that pi is 180. It's way over there. 3 pi over 2, and then 2 pi. This pattern is going to kind of repeat as we go to the left. And so we should end up with a nice smooth curve that looks like this. Going through those maximum and midpoints, almost flat. Again, we have domain. Let's do this now in interval notation, just because we did the other one the other way. So the domain goes from negative pi to pi. The range goes from negative 1, not going to make the same mistake, to positive 1. Square brackets, because we're including a height of negative 1 and we're including a height of 1. And there we go. That is our graph of cosine. They look really the same, aren't they? They're just shifted versions of the same thing. We could probably describe it with a horizontal transformation, and we'll do that a little bit later. All right. Here's the same graph of y equals sine x, or y equals sine theta in this case. It looks a little different. It looks a little flattened only because the scale on the y-axis has changed. We've zoomed out a little bit. This starts off by saying use our transformation skills to predict graphs of y equals half sine x, y equals 3 sine x, and y equals negative 3 sine x. Okay, so those to us, from what we know about transformations, those are all vertical stretch, right? Vertical stretch about the x-axis. The first one is vertical stretch factor of a half. Vertical stretch a factor of 3, and then a vertical stretch factor of negative 3, which we would usually interpret as a vertical stretch factor 3 and a vertical reflection about the x-axis. And so we're going to do all of those things. Let's do this first one. I'm going to do this first one in red. All of the points are going to be half as far up, half as far away from the x-axis as they once were. We've got invariant points wherever we have x-intercepts, because this is a vertical stretch. And we stretch it by a factor of a half, which means we used to have a maximum height of 1, we used to have a minimum height of negative 1, now we have a maximum of a half and a minimum of negative a half. The x values don't change when we talk about this. We just have a vertical stretch, so we are only affecting our y values, and it looks something like that. Whew, that was tight. Oh, go away. All right, let's do the second one. Let's do this in a different color. I'm gonna do this one in green. So y is equal to, we should probably, if we're doing this, we should probably label this and call this y equals half sine theta. We could do that, or maybe we could label this. Sometimes it's easier to, let's describe this one as f of x, so we could call this y equals f of x, and then the next one we could relabel it as g of x, and then h of x, or something like that. But we should label each of these. Y equals f of x. All right, so y equals 3x. No surprises. So this is really not going to look any surprise. We had a maximum height of 1. We're now going to have a maximum height of 3. It's going to stretch it by 3 times. We still have invariant points on the x-axis. We had this minimum here at negative 1. Now we have a minimum at negative 3. And so this will just be stretching this vertically. and all of your invariant points on the x-axis. And sound effects help you draw. So go ahead and do this. I should probably... Oh, that erases all of it. Okay, that's good to know. It was just a little bit wonky there. Oh, that's beautiful. Let's put a little bit of color in there, like the Bob Ross of mathematics. All right, so let's do the third one. Let's do this one as... Let's do this one in orange. I'm going to first, let's label this one y is equal to g of x, is if that's the green one. And then you would define somewhere below the question that y equals 3 sine x, or y is equals 3 sine theta is g of theta, I suppose these should be. All right, anyway, let's do the third one. Let's do this third one in a different color. I'm going to use orange. Is that too close to the red? Probably not. And so let's call this one h of theta. And then if we do that, this is now a vertical stretch of factor of 3 about the x-axis, and it's also a vertical reflection about the x-axis. So it's going to reflect it vertically. It's going to look kind of like the same wave as that last green one, but it is vertically reflected, and so it's going to have maximums where we had minimums. It's going to have minimums where we had maximums. Invariant points, invariant points, just like the word describes, don't change. They are invariant points, and it should look a little bit like that. So those are those three graphs. Use your graphing calculator to verify your predictions. Okay, so it should look right about like that. Part B, sorry, to move on. Compare the amplitude, period, domain, and range, and theta and y-intercepts of the three graphs. What are the same and what is different? What are your invariant points? So now in this table here, we're going to compare with what we have going on here. I used red for this one here. I used green for this, and the last one, no, let's not highlight it. I used orange. Okay. Now, when we talk about the midline with this, we're talking about this line that's not on the graph, but we should graph it, and it ends up being a very important point, a very important part of this graph. So I'm going to draw this in light blue. The midline is the middle height of the line, and it ends up being this horizontal line. We're going to draw this every single time, and this ends up being, in this case, it just ends up being your average height, and we have a height of 3 and a minimum height of -3, so your average is 0, or we have a maximum height of 1/2 and -1/2, so your midline in all three of these cases happens at y equals 0. So that just ends up being your average height of the wave. This is going to relate to, if you want to think about it this way for a second, as a transformation. This would be affected if we had a vertical translation. If we shifted this graph up or we shifted this graph down, this would be a vertical translation. Amplitude is going to describe how high the wave is, but it's not entirely like that. It's not going to be the whole range of this. This ends up being not your amplitude is this whole amount. Our amplitude, so it's not that. Our amplitude is just going to be half of the height of the wave. Okay, so whether you think how much of the wave is above the midline or how much of the wave is below the midline, that ends up being what we call amplitude. With y equals sine x, with the original graph, and I know this is starting to look a little cluttered now, with the original graph we had a maximum of 1 and a minimum of -1. But we had the amplitude goes from your maximum down to your midline, And so your amplitude is 1. In the second graph, when we had half sine theta, our amplitude, our maximum had a height of 1/2, and our midline was still 0, so our amplitude is a half. And as you can guess, our amplitude on this, the green one, is 3, and the amplitude on the last one is also 3. It's not -3. The amplitude is going to be the absolute value. It's going to end up being our A parameter, so we're going to call it absolute A. We could come up with some formulas that help us figure out what amplitude is going to be, and amplitude ends up being the half of the height of your wave. If you take your maximum minus your minimum and you divide it by 2. So 1 minus -1 divided by 2 ends up being 1 in this case. And you can work those out for yourself just to confirm that that ends up being. So we end up with another this extra formula. Maybe it should tie in, maybe a little easier way to remember this is if we look at this midline, that midline is your average height of the wave. How do you find an average in mathematics? You add two things together and you divide it by 2. So if we take max plus min divided by 2, that's going to be our midline. Your average height, it's going to be where this graph is centered around, and then max minus min over 2 is your amplitude equation. Those aren't on your formula sheet, but those are super useful to remember. The period, how long does it take for one full cycle? So if we're looking at the period of this, how long does it take to go through one full cycle? That is all the way up and all the way down. In all three of these graphs, that period ends up being the same. And how long does it take to do one full cycle? To go from 0, it goes up to a maximum, it goes back down, goes down to a minimum, and comes back up. And that has a period of 2 pi. That's going to be the case for all of these. How long does it take to do one full cycle? So period is one full cycle. If you think about it this way, if we're talking about our rotation angles, 2 pi is all the way around. All the way around is one full cycle, and so if we're talking about the height of that point, because we're talking about sine, then all the way around it happens within 2 pi radians. Our domain is going to be all real numbers. For all of these, the fact that we've had a vertical stretch has no effect on what the domain of that function is. And if we've got the range, that's where these are going to start to end up being different. The range goes from -1 to 1. Let's do this in interval notation, just because it's maybe a little bit, saves us some room. Maybe we should have done domain in interval notation. That's okay. -1/2 to half, including those endpoints, because it does get to a height of a half, and it does get to a height of -1/2. -3 to 3 for range. And this last one, the reflected one, it still has a minimum of -3 and a maximum of +3, so the range ends up being the same thing. Y-intercepts, all three of these go through 0, 0. When you're writing, especially if you're using interval notation, you need to be clear about what you're representing, because you can draw a domain or range that starts to look like coordinate pairs, so you kind of have to be careful of how you're labeling what you're writing. The last piece that we're going to get into here is called our midline intercepts. In this case, our midline is along the x-axis. We drew that in that baby blue. So it just ends up being our x-intercepts in this case, but often it's not going to be. Our midline intercepts, it happens, the first one happened at 0, and then the next one was at pi, and then the next one was 2 pi. And so we saw this before where we would draw this we could do this in general form. What we're going to do is we're going to call this pi times n comma 0. The y value is always 0. The x value is some multiple of pi. We need to define that we are talking over the integers. N times pi, where n is an integer. It can be positive or it can be negative, but it's got to be a whole number. Positive or negative wholes, so all of the integers. And that ends up being the same, pi n comma 0. Those are your midline intercepts. Where does our graph cross that baby blue line? And in this case, it's just x-intercepts. And there it is, pi n comma 0. Let's complete this way. That n has to be integral. All right, so moving on. What happens instead if we have this? So use our transformation skills to predict graphs of y is equal to sine 3 theta, y equals half sine theta, y equals sine negative half theta. This is going to look a little bit messy. Let's use the same 3 colors. So let's call this one f of x. I'm going to do in red. And sine 3 theta, thinking of that as a horizontal stretch about the y-axis. That's a horizontal stretch factor 1/3. So all of your points are going to be 1/3 of the distance from the x-axis. So here we have 0, 0. We had a maximum at 0, and it looks like, well, it's pi over 2 was this maximum here, but it was 3 grid marks on this graph, and so this ends up being, that's going to end up be right there, is that pi over 6 is where that is. It's 1/3 of pi halves, right? Here was there's pi comma 0. That's going to be 1/3 of the distance, and so this ends up being just like you would imagine. This ends up being, so 1/3 of so 6 grids. 1/3 of that is 2 grids over. So it's going to go up and down all within just one grid on this. And so then we go down and back up, which ends up making sense that if these are each pi over 6, then this is 4 pi over 6, which is, if we simplify that, that's 2 pi over 3. And if that's 2 pi over 3, that's 1/3 of 2 pi. So that makes sense that that should be 2 pi over 3. That is, erase please. That makes sense that it should be 2 pi over 3 because it's been horizontally stretched by a factor of 3. So we fill this in. This is going to get really crowded. My apologies right now. That was me. I'm going to draw this first one, and then I'm going to erase it to draw the next ones. And it's going to do this super squished kind of graph. It's going to look like regular sine graph, but it's almost like it's been horizontally stretched by a factor of 1/3, which is exactly what's happened. So that's been stretched by a factor of 1/3. That is y is equal to sine 3 theta. Are we good with that? Okay. And to graph the other way, I mean, obviously it would just continue going to the left, and it would be all of that over there on the left side. I'm going to skip over that for now. Let me draw this next one. Let's call that, and we would label that. We would call this y is equal to f theta. In our next color, we did this second one in green. So now we have y is equal to sine of half x. Let's call this g theta. And let's graph sine is equal to half theta. What do we think that would be happening with half theta? That would be horizontal stretch factor of 2. So everything is stretched 2 times as far away from the y-axis. So where we had this x-intercept at pi comma 0, that's now stretched way over to 2 pi comma 0. Where we had it at 2 pi comma 0, that's stretched way over to 4 pi over 0. And everything is going to be 2 times as far away. Pi halves comma 1 stretches to pi comma 1. This point right here, 3 pi over 2 comma 1 stretches to 3 pi. And we end up with this nice, oh, that's beautiful. This nice stretched curve, and we can keep going in this direction as well. There's going to be my new midline intercepts at negative 2 pi and negative 4 pi. We're going to have a minimum that happens at negative pi. We're going to have a maximum that happens at negative 3 pi. And this is going to... Oh, that's less pretty, but I'm sorry. All right, so that's what sine of half theta looks like. It's a horizontal stretch factor 2. And then our last one is going to be a horizontal stretch factor of 2 also, because it's sine of negative half theta. So horizontal stretch factor 2, but also horizontal reflection. So every point is going to be not just stretched, but it's also going to be reflected across to the other side of the y-axis. So this point right here, this maximum is going to be stretched and reflected, and so that happens now at negative pi. Let's put in 0, 0. This one right here is at pi, 0. We stretch it to 2 pi, and then we reflect it over to here to negative pi over 2. And then we could do each of these points individually, or we could now just kind of continue with this pattern, realizing, okay, here I had a negative pi over 2 comma negative 1, so we stretch it by a factor of 2, and we reflect it over the y-axis. And she's going to be right there. This is going to kind of look like the same thing as this green one, but it has been reflected horizontally. I can continue that down here and over to here. All right. So while it does look like it's a vertical reflection, and it kind of is, we can also describe it as a horizontal reflection. Those things have been mirrored in their stretching line. Where was their stretching and reflecting line? That was the y-axis. So if it's a mirror image in that. And that is true. Okay, so now, moving forward, almost done here. If we're wanting to compare, our midline has not changed. Our midline, remember, is just the line y equals 0. And I did mention we should always graph that, yet I've neglected to graph that. Let's go back up here. Let's always graph this midline. Let's do this in baby blue again. And our midline is halfway between our max and minimum heights. So there's our midline, is the line y equals 0. That's going to be a very relevant thing coming up. Super important. Okay, amplitude. What's our amplitude of these? Our amplitude for all of these has not changed. Why hasn't it changed? Well, these all have an amplitude of 1. The distance between your minimum in the median line, or in the midline, and the maximum in the midline, those distances are always just 1. We've treated this graph horizontally only, right? All of these transformations have been horizontal. They've been input changes. So our amplitude has not changed. These are always 1. Remember, we talked about that the midline is your average height, max plus min divided by 2. That is the ugliest looking plus sign ever. I'm sorry about that. And for amplitude, that's max minus min divided by 2. So not on your formula sheet, but certainly super handy to remember. So max plus min divided by 2 for midline, max minus min divided by 2 for amplitude. We could also do amplitude is going to just be that vertical distance maximum minus your midline, or your midline minus your minimum. That also works. Period. Did period change for these graphs? We've affected these graphs which way? These were all input changes. And we, how long does it take to do one cycle? So those have been affected. The period originally was 2 pi for your y equals sine x. And we have stretched this. The first one we stretched by a factor of 1/3. So our period is 2 pi over 3. We stretch that by a factor of 1/3. The next one we stretch by a factor of 2 because our parameter in front of the theta is 2, and so this ends up being 2 times, which gives us 4 pi is our new period. How long does it take to do one full cycle? That's what period is asking. And one full cycle in the green one and in the orange one happens, it takes that long, so it ends up being 4 pi. And then this last one, of course, is also just 4 pi is our period. The domain with all of these, from negative infinity to infinity, this graph extends, it keeps going to the left, keeps going to the right. So with all of these, it's this. And our range, these graphs have been affected horizontally, not vertically. So our range is the same. So why did our range didn't change? Because this was a horizontal change. So why did our domain not change? Well, our domain didn't change because it just keeps going. It's a periodic function that continues on. Once it's done one period of this, it repeats. It's this periodic pattern that happens again and again and again, to infinity to the left and infinity to the right. And that's, I mean, you look at the graph, it's pretty clear to see. So there's your domain. Your y-intercept ends up being, with all of these, it's just 0, 0. Your midline intercepts, that is now going to change between these three things. Our midline intercept for the original on here was every pi. So we're going to call this n times pi, comma 0, where n is an integer. But this is where this gets a little bit tricky. I erased this graph. Remember the red one? The red one that we erased, that was, it was like that, right? What was happening with that graph? That was a horizontal stretch, factor of 1/3. And so if it takes n times pi to get to your first intercept, or it takes pi to get to your first intercept, this is now going to be pi thirds, comma 0 times n. Sorry, pi n over 3, or n times pi over 3, however we want to write this, because it has been stretched by a factor of 1/3. So we're going to take our period, and we divided our period by 3. We're going to take those midline intercepts, and we're going to divide that all by 3. So our midline intercepts for the stretched one, the one that's stretched by a factor of 2, we had a stretch factor of 2. So instead of n pi, we're going to call this n times 2 pi, comma 0, where n is an integer. And then this last one, n times 2 pi, comma 0. Remember, it had the same stretch factor, it just happened to also have a horizontal reflection, where n is an element of the integers. And that, ladies and gentlemen, is our introduction into the graphs of trig functions. All right. Thank you so much. I hope this went well. More is to come. Thank you.